What about the case where you have resistances in parallel? When you put them in parallel, by definition, the potential difference across the resistances is the same, and it's the same as the potential difference across the battery. If you map out the potential everywhere, the potential here is all the same because this is an ideal wire. It has zero resistance, so that's why the potential here, I can put it all in blue color. It's all the same value. But when you go across the battery, you get a new value of potential, and I'll put this as green. All these points have the same potential because all these are ideal wires. So you can see that the potential difference across the battery, which is the EMF of the battery, is the same as the potential difference across the resistor R2, which is I2 times R2, which is the same as the potential difference across resistance R1, which is I1 times R1. So VA minus VB, the potential here minus the potential here, is I1 R1, and it's the same thing as I2 R2. It's the same thing as the potential of the battery. Okay, what is the relationship between the currents? If the current going into the junction here is I, and the current going out here is I1, and here it's I2, what's the relationship between these three currents? We know from the junction rule that the current going into the junction is equal to the current going out of the junction. So this is the simple relationship between the currents. Okay, what we want to do is we want to replace these two resistances that are in parallel by one resistance called the equivalent resistance, and that does the same job. By the same job, what do we mean? It means that for the same battery, it provides the same current I in the circuit. So if you look at this equivalent circuit and you get the potential difference between A and B, it's equal to the current I times R equivalent, which is the same as the potential difference across the battery. And this is what we had for the potential difference between A and B for the resistances in parallel. And this is the junction rule. So now we have all the equations together. So we can use the junction rule here. We know that I here, where is I? I is what? It's delta V over R equivalent. And I1, where is it? It's delta V over R1. And where's I2? I2 is delta V over R2. So we can replace the current I1 and I2 and I in here from these equations, which will give us a relationship between the equivalent resistance and the resistances R1 and R2. Let's flip those equations and write I1 as delta V over R1, and I2 is delta V over R2, and I is delta V over R equivalent. And then we can substitute I here. We can put I2 there, we can put I1 there, and you get the equation. And the potential difference VA minus VB is the same in all cases because it's just the potential difference across the battery. And so all these cancel. And so you have a simple relationship that 1 over R equivalent is 1 over R1 plus 1 over R2.